Welcome to our AP Physics project. Today we're covering 5 major physics concepts: rolling motion, motion of orbiting satellites, torque and work, Newton's second law, and kinetic energy.
We'll explain each concept in simple terms, show formulas, real-world examples, and include demonstrations to help visualize the physics.
By the end of this video, you'll see how these concepts connect to things we use and observe every day, from bikes and cars to satellites orbiting Earth.
Newton's second law explains how forces affect motion. F equals ma. In this equation, force equals mass times acceleration. If force increases, acceleration increases. But if mass increases, acceleration becomes smaller.
For example, pushing an empty shopping cart is easier than pushing a full one. The full cart has more mass, so it needs more force to accelerate.
One, go. When the chair has more mass, it accelerates less with the same push. That directly demonstrates Newton's second law.
This law is also important in cars. Sports cars accelerate quickly because they can produce large forces while keeping mass relatively low.
Rocket launches are another example. Huge engines create massive forces to accelerate the rocket upward against gravity.
Kinetic energy is the energy an object has because it's moving. In this formula, kinetic energy depends on both mass and velocity. Velocity is especially important because it's squared.
That means if velocity doubles, kinetic energy becomes 4 times greater. One or two.
Why is it
1.
0.5? Why is you so...
The faster moving ball has much more kinetic energy and is harder to stop.
This explains why speeding cars are more dangerous. Even a small increase in speed creates a huge increase in kinetic energy during a crash.
Roller coasters are another example. At the bottom of a hill, the coaster moves fastest, so it has maximum kinetic energy.
Work happens when a force causes an object to move. The formula for work is work equals force times distance cosine theta. Work depends on force, distance, and the angle between the force and motion.
If there's no movement, no work is done. For example, holding a heavy backpack still feels tiring, but physically no work is being done on the backpack because it isn't moving.
As the box moves, force is applied over a distance, so work is done.
Torque is the rotational version of force. It tells us how much a force makes something rotate.
The formula for torque is T equals RF sine theta. This means torque depends on the force applied and how far from the pivot point it is.
Think about riding a bike. The pedals rotate around the center. That's the pivot point.
When you push down on the pedal, you're applying a force at a distance from the center. This creates torque and turns the wheel.
If you pedal faster, the pedals rotate more quickly, which increases the bike's speed.
If you pedal slower, the rotation is slower, so the bike moves slower.
But speed isn't everything. How hard you push matters too.
Pushing harder on the pedals increases torque, which helps you speed up or go uphill.
So torque depends on both how hard you push and how far your foot is from the center.
That's why bike pedals are designed far from the center, to maximize torque and make pedaling easier.
Rolling motion combines rotational motion and linear motion.
A rolling object both spins and moves forward at the same time. The incline formula, velocity is equal to radius divided by omega. In this relationship, linear velocity equals radius times angular velocity.
As the ball rolls forward, every point on the ball rotates around its center.
If the radius increases, the ball travels further during one rotation.
That's why larger wheels on bicycles or trucks cover more distance per turn.
Rolling motion is important in cars, skateboards, bowling balls, and many machines.
Orbiting satellites stay in motion because gravity constantly pulls on them toward Earth.
Instead of falling straight down, satellites move forward fast enough that they continuously fall around Earth.
When satellites are farther from Earth, gravity becomes weaker.
The satellite changes orbital speed. Satellites closer to Earth move faster because gravity is stronger there. Is that good?
No.
The string pulling inward acts like gravity for a satellite. Without the inward force, the object would fly off in a straight line.
This gravitational force depends on the masses and the distance between them.
Today we covered Newton's second law, kinetic energy, work and torque, rolling motion, and orbiting satellites.
These concepts explain why many real-world situations, from transportation and sports to space exploration, all are related to physics, rotational kinematics.
GPS systems, weather forecasting, and communication satellites all rely on orbital motion.